Hello, today we are gonna prove one of the lemmas concerning semiring. Let A1, An be sets in the semiring sigma. The sets from A1 to An are subsets for the set A. And the sets from A1 to An are mutually disjoint. Then there exists sets from An plus 1 to As, which belong to the semiring sigma, and they are such that A equals their union. So A equals A1, the union of the sets from A1 to As. And the sets from A1 to As are mutually disjoint. We will prove this lemma by induction. So for the case when n equals 1, the lemma follows as from the definition of the semiring. So the case n equals 1 is clear. If n equals m, we assume that the claim is true. And now let's show that the claim is true also when n equals m plus 1. So let's take sets A1, am plus 1. Let's assume that they are mutually disjoint and they belong to the semiring sigma. Because the inductive hypothesis tells that the claim is true for the sets for many sets. So for the sets from A1 to Am, we can find B1, Bp, so that all of them belong to the semiring sigma, and they are such that A1 union Am union B1 union B, P equals A, and we will denote this equation by star. So let's make also the following notation. Am plus 1 intersected with BQ. Let's denote this intersection by BQ1 for each Q from the set of the numbers from 1 to P. And once again applying the definition of a semiring, so BQ1 obviously belongs to the semiring sigma, and BQ1 is a subset for BQ. Therefore, by the definition of a semiring, there exists BQ2, BQRQ, all of them from the semiring sigma, so that BQ is equal BQ1 union BQ2 union BQRQ, and all of these sets are mutually disjoint. Now, it will be easy to see that A equals Am union Am, A1 union Am union Am plus 1 union Q changes from 1 to P, and J changes from 2 to RQ, BQG. So it is easy to see that A is the union of the following sets, is the following union. And now let's discuss why each of the sets participating in the union, all of these sets participating in the union are mutually disjoint. So we have taken the sets from A1 to AM to be mutually disjoint from the beginning. And because we have this equation star, this means that A1, AM, B1, BP are mutually disjoint. Yes, we have stated that those sets are mutually disjoint by the inductive hypothesis. Therefore, AM are mutually disjoint with all of the subsets of these sets from B1 to BP. Therefore, AM, etc., AM, and all of this BQJ, they are mutually disjoint. The only thing which is left to see is that AM plus 1 and all of these BQJs are mutually disjoint. So let's assume that for some Q from 1 to P, and for some J from 2 to RQ, AM plus 1 intersected with BQJ is not equal to the empty set, but considering that AM plus 1 intersected with BQJ is a subset for AM plus 1 intersected with BQ, which is exactly BQ1 by our notation, we will see by this assumption that BQ1 intersected with BQJ, and J changes from 2 to RQ here, is not equal to the empty set, which is a contradiction. Therefore, the claim is true for n equals n plus 1, and we have proved the lemma.